Hello everyone. Welcome to Homework 1, the first lecture for the class, talking about rounding, estimation, fractions, and decimals. So what I do with these lectures is I go through some of the homework problems, explain the process. I go through a different problem each time, so you have an idea for any kind of problem within the homework assignment, but I leave some there that require some thinking for you. So for this section, pretty basic section in terms of math. We're going to talk about some basic arithmetic things like rounding and estimation. That's important in the cooking world, depending on what you are cooking. You know, some things require exact numbers, some things don't. You kind of go, meh, yeah, good enough. So let's talk about the number system in general first before we get into everything. So the number system is made up of several different sections. First, you have what we call the natural numbers. Now, this isn't in your homework, but I like to start off the math classes like this because it gets our basic understanding of where everything's coming from. Natural numbers are the numbers that you can see in nature, you know. You can see them in whole amounts. So if you have like one cell phone, two cell phone, three cell phone, four cell phones, right? You got one cake, two cake, three cake, four cakes. That would be the natural numbers. 1, 2, 3, 4, 5, and so on. They go on forever as counting numbers. Whole numbers would be the next one. Whole numbers are exactly like natural numbers, but they have one extra number in there, which would be the number 0. And then after that, it still counts up. Then after that would be the integers. Integers is the next set of numbers. Integers are just like whole numbers, but it includes the other side of the spectrum, which would be the negative numbers. So integers go like this. They go -3, -2, -1, 0, 1, 2, 3. And as you can see, they continue on this way and they continue on this way. So they go on forever in both directions. Difference is they're still counting numbers. They're still whole numbers. That's what an integer is. It's a whole number. Then we move into rational numbers. And all of these are part of the real numbers. Rational numbers are anything that can be represented as a ratio. So rational numbers, think fractions or think decimals. So rational numbers could be 0.5. I could have something like 1 over 3. I could have something like 5 over 6. I can have 3 and 1/2. That's a rational number. More rational numbers are numbers that are whole numbers too. They include integers and whole numbers. So I could even have -5. I could have 100. I could have 0.456. That would also be a rational number. Other examples of rational numbers are repeating decimals, ones that have patterns. As you know, 1/3 equals 0.333 repeating. It goes on forever. And we write this as 0.3 with a line over the 3. The line over the 3 means the 3 repeats. So if I have a number like, let's say 1, 2, 3, 1, 2, 3, 1, 2, 3, we can see that the 1, 2, 3 is what's repeating, so we can write that as 1, 2, and 3 are repeating. You might even have a number like, let's say, 1.14444444. Notice the 4 is the only thing that repeats, so we would go 1.1, and we'd put a line over the 4 only, because the 4 is what's repeating. So if it was like 1.1454545, we would say the 4/5 is repeating. So rational numbers are any number that can be represented as a fraction. These three numbers right here can also be represented as fractions. There's a way to figure that out, but we're not doing that in this class. But they can be represented as some kind of fraction. Now, rational numbers can be repeating decimals. They can also be terminating decimals, meaning they don't go on forever. They can be whole numbers or integers. It doesn't matter. They're always a repeating or terminating decimal. So the next one would be irrational numbers. Irrational numbers are numbers that are decimals that do not repeat in some kind of given pattern. So if we look at something like the number pi, so let's talk about pi. You might be familiar with pi, 3.14. So pi looks like this. It's kind of like that. We approximate it to 3.14, but pi equals a very large number that goes on forever and ever. So it's not necessarily a large number, but it's an infinite number. So here are some of the digits: 3.1415, 9265359, dot dot dot. And as you can see, there isn't any kind of pattern going here with the decimals on the right side. So we can't figure out a fraction for it. There is no fraction. It's an irrational number. Also, an irrational number would be something like the square root of 3. Square roots, most of them don't have a repeating pattern. So if I take like square root of 3, that approximates to 1.7320508. There's no set of numbers that's repeating. But be careful, because if you have something like a rational number, let's say I have the square root of 9, square root of 9 actually equals 3, which makes it a rational number. Even like the square root of 4 equals 2. We're not going to go over square roots at all in this class, but I just wanted to tell you that that's what it is. So if something simplifies, it can simplify into a rational number, but this one doesn't simplify. It simplifies into a repeating decimal, goes on forever and ever. So if we were to like put all these things into one graphic diagram, let's say I draw like a rectangle. I need my little shape tool. Say I draw a rectangle, and we can represent everything in terms of all the different types of numbers. So first off, irrational numbers and rational numbers are never the same. So I can separate this, and I can say this is the irrational numbers. This represents a rational number. Rational numbers also happen to be, me drawing a square this time. Rational numbers also happen to be integers. And integers, not all integers, but all whole numbers happen to be integers. And then all natural numbers happen to be whole numbers. So you can see natural numbers are also whole, integers, and rational numbers. A whole number is also an integer and a rational number. All integers are rational numbers. But rational numbers are just rational numbers. So rational numbers aren't necessarily integers and whole and natural numbers. All of this represents the real number system. In a college algebra class, you'll be working with imaginary numbers or complex numbers. That's a whole different ballgame. We're not going to be touching that at all in this course, but you will be talking about something called the complex number system if you decide to take a college algebra course with your bachelor's degree, if you happen to go for the bachelor's degree. So let's talk about place value too. Let's talk about the place value of numbers. I'm going to just write down a big old number. Let's say I write down 1, 2, 3, 4, 5, 6, 7. Not terribly creative here. 1, 2, 3, 4, 5, 6. We can label each place value in this. You might be familiar with everything on the left side of a number, where this is the millions place, right? $1 million. Got a million there. Whereas the first number would be the ones place. This would be the tens place. This would be the 100ths place. This is the 1000s place. This is the 10,000s place. This would be the 100,000s place. And then this is the millions place at the end, right? Keeps going up for every 10. Whereas on the right side, we start out with the tenths place. Has an S right there on the end. So the THS on the end, tenths place. That'd be the tenths place. This would be the 100ths place. This would be the 1,000ths place. And it keeps going 10,000ths place. This would be the 100,000ths. That would be the millionth place. You need to know the place value so that we know how to round numbers. So for instance, let's look at some questions from the homework. This is related to like number 2 on the homework. Now everybody might get a different number on the homework. They might be generated as different numbers. That's all right. You might even get the same number I have as I do an example on here. On number 2, it wants us to round 318 to the nearest, I'm paraphrasing here, nearest 10 place. So if we're rounding to the nearest 10 place, we have to examine the number 318. This is the ones place. This is the tens. This is the 100ths place. So we have to round it to the tens value right there. So in order to round, whenever we round numbers, if I want to round it to this number right here, this is my dividing line. We think of this as a little dividing line. This number right here is either going to round up or it's going to round down. And it all depends on this number right here, that 8. So the 8 tells us if we round the number up or down. If your number is 0 through 4, you round, I'll put in quotes, down, meaning we keep it the same number. So that would mean this 1 would stay the same. It'd stay as a 1. If your number is 5 through 9, you round up, meaning we would have to round the number to the next number. We round this up 1 number. So since the number 8 is in this category, it's in between 5 and 9, we're going to round the number 1 up. So this number is going to end up be rounding up, and that would make the number 320. That would be your answer rounded to the nearest tens place. So we rounded it to the nearest tens. If we were to take that same number, 318, and it says round to the nearest hundredths place, I will say 100. Well, we're going to take the number 318. The hundredths place is the 3. So, oops, I deleted one more. So our dividing line would be right here. The 1 determines if we round it up or down. Since 1 falls into this category in between 0 and 4, we will round this number down, or rather, it would stay the same. When we say round down, we keep it the same. This would mean 300. Let's try another one on the homework. I'm going to pull up several different examples from the homework. Let's say number 3. It says round 7,924 to nearest 10. So 7,924. The tens place is where the 2 is. Remember, this is 1, 10, 100, 1,000. So this is a dividing line. Since this number right here is in between 0 and 4, we're going to round this number down, and that would make this number 7,920. Now, if that problem said round nearest 100, say 100, we're going to take 7,924 and round to the nearest 100. That means 100 is right here. It's the 9. So our dividing line should be right here. This number determines if we round it up or down. So we round the 9 down because it's a 2. So we keep it the same, 7,900. Now, notice all the numbers to the right always become 0. Like this became 0, these became 0. Whenever you're rounding like that, you always round all the numbers to the right as 0. What if it said round to the nearest 1,000? 7,924. Nearest 1,000 would be the 7. So this is our dividing line. This number tells us to round that up. So that number would then be rounded to 8,000. So that's how to round with like different place values if your numbers are whole numbers. All tens, hundreds, and thousands. So let's talk about something like a decimal, like number 8 on your homework. It wants us to round to nearest 10th. Oops. It wants us to round. Let me scoot that over. I forgot to put the number in here. Round 9.52 to the nearest 10th. So let's take 9.52. The 10th place, remember, would be the first number to the right of the decimal. So this is our dividing line because this is our tens place right here. Because of this number right here, it's between 0 and 4. We're going to round this number down. And this number would become 9.50. That would be your answer. Now, in the decimal world, you don't need zeros after numbers to the right of the decimal. And I'll explain that here in a second. I just want to give us another example. Let's say we have number 10. It says round 505.054 to the nearest 10th. So 505.054. The 10th place again is the 0 in this case. This is our dividing line. So this number right here is 5 to 9, so we need to round this number up. So this would become 505.1. That would be our answer. What if it said round to nearest hundredths place? 505.054. Hundredths place happens to be where the 5 is this time. So this is our dividing line because this is the hundredths place. This number right here is in between 0 and 4, so we round this number down. This would become 5. Well, I'm not going to put the equal sign because we're rounding. 505.05. And that would be our answer. So notice on this one, I didn't put the 0 and the 0 right here, and I didn't put the 0 right there. Because with decimals, you don't necessarily have to put a 0 to the right. Let me show you what I mean by that. If I have like the number, let's say 5.25, I could actually say 5.250 is the same thing. 5.2500 is the same thing. 5.25000 is the same thing. I can have as many zeros as I want to the right of the decimal. And the decimal's right here. I can have an infinite amount of zeros or trailing zeros at the very end as I want. What you have to watch out for, though, is what if I have, let's say, 4.025. This 0 right here is different. It has to be there. You can't put zeros in there, right? You can't say something like 4.00025. That just changes the number completely. So you can't have that. You can, however, have 4.025000000. You can put zeros on the end. Now, we don't usually do all of this, of course, but you can, and it's an option. But what you need to know is that those can mean the same thing. If I have 125.5, that's the same thing as 125.50. But think about the other way. What if I have 1,250? Well, I can't take away the 0 and make it 125 because these two numbers are not the same number, right? I can't take like the number 425 and I cannot add zeros on the end because that changes it, right, to 425,000. You can only have all these trailing zeros if they're on the right side of that decimal right there. So you got to look out for the decimal right there. Zeros on the right side of the decimal are fine. Zeros on the left side, they make the number different. So just watch out for that whenever you're doing all these rounding numbers. Let's try another example on the homework. What if it says on number 12, it says round 155.862 to the nearest whole number. So as we learned, whole numbers are like solid numbers. They're not fractions or decimals. They're whole numbers, right? They're an entire whole. There should be no decimal. So the whole number for this would be where the decimal is. So this is the line of like demarcation of numbers of whole numbers and fractions. So we need to round this number right here, the 5, up or down. Since 8 is in between 5 and 9, we're going to round this up, and that makes it into 156. That would give us our answer for that one. Well, this number, let's say, I'm looking for the penny one. There's a problem here with pennies and cents. This is number 15. Round to the nearest cent. If I have the number $83.0171, you can have something like this, like whenever you're calculating an Excel spreadsheet, when you're talking about taxes, profits, anything, every exact number matters, right? You know, whenever you have interest in a bank, you want them to include as many decimals on this side as possible if you want to gain more money in the savings account. And then the other side, you know, if you have a credit card account and you owe interest, of course they're going to calculate all the extra cents on the end, so you end up paying more in interest. Now it wants us around the final, like after they get this number, right, after they add up all your numbers on your savings account, they might get a bunch of decimals off to the right side, which is fine, but then they just take this number and round it to the nearest cent. Nearest penny would be right there where that 1 is. Since this number is higher, it's 5 through 9, we need to round that up a penny. So your answer would then become $83.02. That gets a little tricky with all of that. Let's go back, and I'm going to go back to a couple of other problems where we talk about something called the principle of estimation. This is number 6. So whenever you want to estimate something, you round everything to its highest place value. So for instance, 752 plus 339 plus 234. The principle of estimation says round everything to its maximum point value. So meaning here, the maximum is a hundreds, hundreds, and hundreds place. So we need to round each one of those numbers to the hundreds place. 752 would round to 800. 339 would round to 300. And 234 would round to 200. We rounded everything to a hundreds place. You would then add up all those, and that makes 1,300. Let me scoot this a little bit to the right. Because what we want to put, whenever we're rounding, I'm going to put this little squiggly equal sign. A squiggly equals means like, yeah, you know, it's about equal to. It's about equal to that. I mean, it shows that we rounded and we estimated. Whereas equals means that's what it equals, because all of this does equal 1,300. But all of this was approximated. So it's kind of like a pathway. Oh, from here to here, we approximated. And then from here to here, we actually did an exact calculation. So that'd be your answer. Number 7 is similar, but the numbers are a little larger. It wants us to use the same thing. 104,700, so 104,700 plus 86,572. Erase this little mark I made. And then plus 3,624. We're going to approximate each and every one of these to its largest point value. So here would be the hundred thousands, here would be the 10,000s, and here would be the thousands. So 104,700 would round to 100,000. 86,572 would round to 90,000. And 3,624 would round to 4,000. All of that added up together comes out to 194,000. So as estimation, I mean, usually whenever you're estimating things of this nature, like this one isn't too bad. This one is, that's a harsh estimation. It really just depends what you're gauging. And me, it depends on the circumstances, right? I'd rather overestimate something than underestimate something, in my opinion, for, I don't know, anything. It could be anything with like, oh, my budget for purchase of food for a catering event or something like that. Maybe I just need a little extra money just in case, even though I've calculated all my costs to be a certain amount of money. I might want to, overcalculate, overestimate just a little bit, just in case I need some of that spare change. I do that for packing for trips, right? Oh, I always overestimate how many clothes I need. I always pack too much whenever we're going on vacation. But I'd rather overestimate in that sense. Underestimate, you want to underestimate in certain categories, right? Oh, I want to underestimate, the amount of work something might be for something that's considered easy. It might be easier than you think it is, but underestimating, overestimating, it just depends on what the situation is. But something drastic as like number 6 and number 7 in terms of numbers, I don't see where entirely that would become, I guess, very well used in any kind of environment. Because I mean, rounding 104,000 to 100,000, that's knocking off 4,000. Whereas here we're gaining 400. That 400 doesn't make up for that 4,000 necessarily. And then here we're knocking it up about 3,500. So rounding all these numbers, it gives you a very rough estimate, because if you added all those numbers up, it would make a different number. So if you added up 752 plus 339 plus 234 for the first problem, this one would actually equal 1,325. Whereas for this one, if you added up 104,700 plus 86,572 plus 3624, that would give you 194,896. So this one right here was off by like 25. This one right here was off by 896. Obviously more, that's because the numbers were rounded more harshly in the second one. It all depends. Is 896 something, big to deal with? Are we talking about money, or are we talking about like, ounces? 896 ounces. That's got a lot of ounces. Depends what you're talking about. Talking about milliliters. Oh, okay, it's almost a whole liter. Really just depends what the context is. So estimating, I only recommend it if you're trying to do something quick. If you're trying to give something like, oh, the distance from here to, I don't know, Sal Padre, it's about 4.5 to 5 hours. That's an estimation, and that's harmless. No one is going to, crucify you for going, saying, no, I didn't get there in 4.5 or 5 hours like they said. I got there in 6 hours. It's like, well, they'll be fine. All right, something estimating like that is fine. But if it's money and it's like, oh, no, I'm short $896, kind of a bigger deal, right? And it really depends on what scale we're talking about. So let's try something else. Now let's talk about making fractions into decimals. So let's go back to long division. Let's talk about number 17. It wants us to change 9 over 10 to an equivalent decimal. Now you can go on your calculator and do 9 divided by 10. And if you're not familiar, top number is called a numerator. Bottom number is called a denominator. The denominator. So this fraction line right here represents the difference between the numerator and the denominator. What fraction of a whole is it? You can also use it as division. So we could actually divide 9 divided by 10. So to find out what that number is, we're going to go back to our old school math. 9 would be the top number. 10 would be the bottom number. So this is the dividend. This is the divisor. It's dividing into the dividend. The one being divided. And this is our little fraction line, the little house. You might remember that. They say, oh, take the number, put it inside the little house right here. And that gives us our number. So 9 divided by 10. Before I get to that, let's try like a very basic example. Let's say I have 8 divided by 4. Our rule for long division is, oh, how many times does this number go into that number? 4 goes into 8 twice. So we put a 2 here. And we check 4 times 2 makes 8. That's what we're going to subtract from the bottom. If I did 10 divided by 4, we'd say, oh, 4 goes into 10 twice, so we put 2. 4 times 2, or multiply those two numbers together. That makes 8 again. That's what we're going to subtract from here. And then we don't do the remainder. We don't say 2 remainder 2 anymore like you would do in grade school. What we do now is we introduce a decimal at the end, stretch this out a little bit, and line up the decimals right here. We add a 0 on the end of the decimal because remember we could add as many zeros as we wanted. Bring down the 0. 4 goes into 20 5 times. 4 times 5 makes 20 and 0. So 2.5 is your answer. So going back to our problem of 9 divided by 10. 10 doesn't go into 9 at all, so we have to introduce a decimal and add a 0. Line up these decimals on the top and the bottom. You can put a 0 here to say 10 did not go into 9 at all. Now 10 goes into 90, the whole number, 9 times. 10 times 9 makes 90. Subtract 90. That gives us 0. That would be your answer. So 9 over 10 can be converted to 0.9 as a decimal. Let's try number 18. For mine, it wants us to convert 3 over 8 into a decimal. So we say 3 divided by 8. 8 can't go into 3, so we have to put a decimal and a 0. Decimal and a 0. Put a 0 here to oops, not doing the 0 on the right side. Put a 0 here. 8 goes into 30 3 times. 8 times 3 is 24. Subtract 24. 30 minus 24 is 6. Keep going. Add a 0 until we have an answer at the very end, or if it repeats. 8 goes into 60. 8, 16, 12, 13, 40, 48. 56, 7 times. Subtract 56. Bring down a 4. Looks like we had to add another 0. 8 goes into 40 5 times. 8 times 5 is 40. That makes 0. So that means 3 over 8 converts into 0.375 as a decimal. All this long division process. Come back to grade school, when we would do all this long division by hand. Let's check out number 20. Let's just say approximate this one. 6 over 13. It wants us to round to the nearest thousandth. Probably because it's going to repeat. So let's do 6 divided by 13. 13 can't go over to 6, so we have to add a 0. So how many times does 13 go into 60? It goes into it 4 times evenly. So this would be 4. 13 times 4 gives us 52. We're subtracting 52. Subtract those out. That gives us 8. Bring down a 0. 13 goes into 80 6 times. So this would be 6. And 13 times 6 is going to be, 13 times 6 is going to be 78. Subtract 78. to bring down another 0 and to keep going. It says 13 goes into 20 one time. Subtract 13 from there. Oops, my tablet. That gives us 7. Now, as you can see, we currently have tens, tenths, hundredths, thousandths. But we have to go one more number off to here because we have to see if we need to round this number. That's why it says round the nearest thousandths. We don't stop at the thousandths. We have to find out the next number. So we need to find out one more number. Bring down yet another 0. 13 goes into 70. That would be probably 5 times because the last time we had was 78 earlier. So 5 times. 13 times 5 makes 65. This is a 5. So now we see that we went all the way to the 10,000ths place. So 6 over 13 about equals 0.4615. But remember, we have to round it to the nearest thousandths. So we needed that 5 right here on the end because that causes this number to round up. So our answer would be 0.462. That would be our answer for rounding it to the nearest thousandths place. So you have to go one step further to the right in order to get the rounded answer. So that's what you would do whenever you're approximating decimals. Let's do like an example. Remember I said that 1/3 earlier? Sometimes you might see a pattern of some sort. What if I have like 1 over 3? Well, if we were to actually divide 1 divided by 3, some of you might already know what it is, as I discussed earlier. Have to add a 0. So 3 goes into 10 3 times. And then we have to have 1. Bring down a 0. 3 goes into 10 3 times. That makes 9 again. Bring down a 1. And as you can see, this process keeps going. So what you normally want to do for some of these long division problems is look for a pattern. Once you establish a pattern, you can then just say it repeats. So there are some numbers that repeat over and over again, depending on what it is. Usually odd numbers will do that. So if I have something like, if I had 2 divided by 9, that would make 0.22222. I need to have a repeating one though. One that's, let's try this one. Let's approximate 2 over 11. Without a calculator, let's do it by hand. 2 and then 11. It cannot go into 2, so we put a 0 there. Now 0. 11 goes into 21 time. Subtract 11, that gives us 9. Add a 0. 11 goes into 90 8 times, so that makes 88. That makes 2. Oh, there's that 20 again. 11 goes into 20 one time, so that makes 11. And you can see the cycle repeating in the division. So if I mark them off with different colors, here we subtracted 11, here we subtracted 11, and then here we subtracted 88, here we subtracted 88. But you can also look at your resulting numbers instead. You can say, oh, I got 90 here, I got 90 here, and then here we were going to get 20 here, and then 20 here. You see where the pattern occurs, any kind of pattern, but you can see that they alternate. So the numbers being subtracted here and here and here and here alternate, or the end numbers, the result numbers, 90, 20, 90, 20, those alternate as well. So if those alternate, these numbers will alternate. It's a pattern. So now that you can see that the pattern, 1/8 is a number repeating, we can say 0.18, the 1/8 is a repeating number. And that would be the answer for that. Okay, let's try number 24, which is a word problem. And I'll wrap it up for this. Number 24 says, bag of potato chips. On my end, it says a bag is 40 ounces. but the serving size for the bag of chips is 1.25 ounces. It wants us to find the estimated, so find the estimated servings per bag. Now, to find the estimated, remember that principle of estimation we had, we want to take the number 40 ounces and 1.25 ounces, and we want to estimate each one of those to its highest unit of measurement. So here we have to separate here, and here we separate here. 40 rounds to 40, it stays the same. 1.25 would round to 1.00. Then define servings per bag. Whenever we see this number per, we want to think about a fraction. So we want to do 40 divided by 1.00, which gives us 40 servings per bag. And that's a rough estimation, because then if we do the exact estimation, what it asks for in the next step, we would then do 40 ounces divided by 1.25 ounces, and that gives us a different number. That gives us 32 servings per bag. So you get different answers for each one of those. So the principal estimation, as you can see, 40 servings is 8 more servings than 32. And, it depends. Is that a big deal or not? I mean, is that a lot more chips? I'm not terribly sure how much chips weigh, so I don't know how many chips that is in terms of 1.25 ounces. All I know is it's about a 15th, close to a 16th of a pound. That's about it. But anyway, it just depends, again, what you're doing. I find 40 servings and 32 servings would be drastically different in my opinion, but that's just me for math and grocery shopping. All right, so that wraps it up for homework 1, lecture 1. Go ahead and attempt that homework if you haven't already. Getting some basic stuff. We'll talk about unit conversions and everything. See that ounces and then per serving. All that's going to be after quiz 1. So don't worry about like this per ounces per serving and stuff. We're going to be doing that later on. The next section is going to be over homework 2, which I believe we start getting into a little bit of algebra stuff. So we'll be getting into homework 2, signed numbers. So we'll talk about adding and subtracting negative numbers and a bit of algebra with algebraic expressions. Go ahead and tackle the homework and go on to the next lecture for next week.